The first talk is by Juan Ha on external energy paradigm for black holes.
Okay, so I'd like to present a new result, which is possibly even revolutionary. And the title is External Energy Paradigm for Black Holes. So now we know that black holes and gravitational waves are the new frontiers in astrophysics and cosmology. And the discoveries at LIGO, assuming the data are correct, right, will lead us to new concepts in understanding of black holes. Now here we take a look at the first detection of gravitational waves in 2015. The primary black hole has a mass of 36 solar masses with spin parameter 0.32. Secondary black hole has 29 units and spin parameter 0.44. And the final black hole has a bigger mass, 62 units, and spin parameter 0.67. Now, so we conclude that from these masses that 3 units of gravitational waves are released from the merging. Now, this is very fine if we look at these black holes from a great distance. Now, however, we know that these waves are produced during the merging near the horizon of the black holes. Now, so they are severely redshifted. So, so in this case, if you believe that the waves have energy of 3 units, then where's the missing energy in the redshift? Now, so that's a little mystery here. So what we need is actually the mass at the event horizon of these black holes. Now, according to my investigation, the primary black hole has a mass of 71 units at the horizon. The secondary black hole has a mass of 57 units. The final black hole has 116 units. Now, so when we use these masses, we can see where the missing energy is. Now, so the released energy is 3 units, and these are the waves we believe they propagate to infinity. And the redshift energy is also 3 units, and there's a remaining 6 units for uncertainties. Now, so the concept of the mass at the horizon is important. Now, for investigating these black holes, we need to use the Kerr Metric from 1963. Now, here I show the solution, the metric explicitly in physical units, so that we can read off the metric components very easily. And we need this a little later. Now, so here we have a length unit given by small m, gm over c squared, and capital M is the physical mass. Now, we know that this solution is exact. It's unique for a rotating mass, and it's also a stable solution. So it is the only solution for a rotating mass. Now, so if you don't believe this solution, then there's nothing to believe. Now, we also need to use the rotation parameter, which is given by this. Now, we have one which is angular momentum length parameter, alpha, defined by this, a simple definition from mechanics, and also a dimensionless spin parameter used by LIGO. This we call 8. Now, so this number is dimensionless. The first number, alpha, has a length dimension, and we can convert them very easily. Now, in 2005, I derived a theorem for all black holes, which I call the horizon mass theorem. And the theorem states this: for all black holes, neutral charged or rotating, the horizon mass is always twice the irreducible mass observed at infinity. So it has a simple relation like this. Now, so just for people who have not heard this before, so the horizon mass is the mass which cannot escape from the horizon of a neutral charge or rotating black hole. It is the mass observed at the horizon. Now, the irreducible mass is the final mass of a charged or rotating black hole when its charge or angular momentum is removed by adding external particles to the black hole. And the irreducible mass does not contain electrostatic or rotational energy. It is a mass observed at infinity. Now, so here we have the formula for the irreducible mass of a rotating black hole. Now, this was first derived by Christodoulou and Ruffini in 1971. Now, Christodoulou was 19 years old and Ruffini was 28 years old. Is that correct? So here's the reducible mass formula, a wonderful result. And the difference between the Kerr mass and the irreducible mass is the rotational energy of the black hole. Now, if we put the factor of 2 in front of the irreducible mass, then we derive something with great meaning, and it becomes the horizon mass of the black hole. Now, so what this means is electrostatic energy and rotational energy of a general black hole, they are all external quantities. They are absent inside the black hole. Now, a charged black hole actually does not have electric charges inside. And a rotating black hole does not have any rotation inside either. Only the external space is rotating. Well, so this means that electrical particles cannot exist inside the black hole. They can only stay at the surface. And for rotation, similarly, the rotational energy is external, and particles with angular momentum cannot exist inside the black hole either, and they must also stay outside. Now, for elementary particles with a spin or charge, this means that they cannot exist inside the black hole. Now, for us, we know all matter particles are fermions, which have a spin or a charge. These are the quarks and leptons. Therefore, matter cannot exist inside the black hole and has to stay outside also. Now, this was what I discussed last year also here. Now, according to Tomonaga, nature was not satisfied by a simple point charge, but required a charge with spin. Now, this is always the case. Now, for the Higgs boson, there's no charge, and therefore there's no spin. Now, so for these reasons, I come up with this external energy paradigm for black holes, which can be stated this way. All energies of a black hole are external quantities. Matter particles are forbidden inside the black hole and can only stay outside or at the horizon. And these energies include constituent mass, gravitational energy, electrostatic energy, rotational energy, heat energy, etc. Now, so we would like to understand why energy is forbidden in the black hole. Now, the first reason is this: space and time are interchangeable, interchange inside a black hole. And since energy dimension is always defined as mass times length squared divided by time squared, so in the interior of the black hole, it becomes mass times time squared divided by length squared. And And this dimension is unknown in physics. So this is certainly not possible. Now, for elementary particles, we also understand this. Particles exist only in flat space-time in quantum field theory. Now, black holes have strong space-time curvature. And according to Wigner, elementary particles belong to irreducible representations of the Poincare group. And for fermions, they belong to spinor representation of the Lorentz group, SO31. And there's no spinor representation of the group of general coordinate transformations, which is GL4R. Now, so fermions can only exist in the tangent space, in curved space-time. Now, if the tangent space is too small, then the fermions cannot exist. Now, another reason is quantum particles are actually extended particles with a size given by the Compton wavelength. Now, so here's the Compton wavelength. Now, they are called point-like particles only because they are described by local interaction terms at the same point in the Lagrangian, such as the current gauge interaction. Now, so they are not really point-like particles. And even up to now, it is not clear how quantum particles will, with helicities, will move in Schwarzschild space-time, or whether they follow the geodesics of classical point masses. All particles in nature are quantum particles. The conclusion that matter particles can cross the horizon based on the Kruskal diagram is actually questionable. Now, we don't really know what happens.
You can read it the other way around. That's the problem of the black hole, not so much.
Okay, well, we'll...
Assume this given. Right, with me, but I don't believe a word of that.
Well, I know you don't believe in black holes either.
No.
Right. Okay, so let's continue this. Well, I'm giving them. Okay, now next we consider the Reissner-Nostrom black hole. A Schwarzschild black hole becomes a charged Reissner-Nostrom black hole even with the addition of a single electron. And the electron must stay at the surface according to the property of Reissner-Nostrom black hole, right? Because charge cannot be separated from the mass. So the electron cannot exist inside the Schwarzschild black hole. Now, all those are rather clever reasons, but the most compelling reason why particles cannot exist inside black hole is the next one. It is a simple physical reason that defies the imagination of many physicists. This is the reason. The Schwarzschild black hole is actually a hollow, massive shell. And all mass is located at the surface. The surface becomes the horizon, and the extreme density of the surface prevents external particles from crossing the horizon. Now, this is the reason I'm going to prove to you. So what this means is we're going to establish the black hole as a real physical object with a distinct boundary. And there's no singularity inside the black hole because matter cannot enter the black hole. Now, for LIGO, the collision of the two black holes is modeled by the collision of two extended bodies. It is not modeled by the collision of two singularities. And the signals suggest that, show that the dominant wave emissions stopped as soon as the horizon merged. Okay, so here's the proof from the Kerr rotation of that result. Now we're going to start from the basics. So here's the definition of angular velocity, omega, the rate of change of the angle phi with time, and they're given by the metric coefficients, gt phi over g phi phi. And after some calculation, you can arrive at this general result. And the delta is defined here. Delta is here and here. Now, so this is a very complicated expression for the angular velocity. Now, however, it can be simplified quite a bit at the event horizon. So when the coordinate becomes the horizon radius, there's a great simplification, and it becomes the angular velocity at the horizon. This is the angular momentum parameter, and this is the horizon radius and the angular momentum length parameter. Now, even so, the expression is very complicated. Now, so here's the horizon radius from the Kerr metric. So here's the mass, the physical mass. Here's the angular momentum J, and so on. And when we substitute this in the previous expression, we will arrive at this angular velocity at the horizon. Now, so here's the angular momentum, and also here, and the mass, and so on. Now, so this is still very complicated. Now, however, this is an exact relation. It shows the angular velocity depends on the angular momentum and the mass in such a way. Now, if this is a relationship, then we can also do it the opposite way. We can show that the angular momentum depends on the angular velocity too. Now, so we're going to invert this using quite a bit of algebra, and we come up with this basic result. So we come to the moment of inertia of the rotating black hole. So the relationship between angular momentum and angular velocity defines the moment of inertia in this way. Now here the moment of inertia depends on the angular velocity also. Now, after a lot of work in algebra, and also using a special combination of these terms, we can arrange the angular momentum to depend on the angular velocity in such a way. Now, this is much better than before. This becomes a length here. Now, this mass is the Kerr mass with rotational energy. Now, so this is the same length, and this is also the angular velocity here, omega squared. So angular velocity is here and also here. Now, in the limit of zero rotation, the angular velocity becomes zero. So we can set this omega squared to be zero first. And therefore, we will remove this term, and we'll end up with just the terms in the numerator. Now here we still have the rotational energy. Now, so as the rotation stops, the mass will become the irreducible mass. So the moment of inertia will become the mass, irreducible mass, times the length here, which is the Schwarzschild radius of the black hole. Now, so this part is the moment of inertia of the Schwarzschild black hole. It has a very simple structure now, just Schwarzschild mass times Schwarzschild radius squared, and this is the moment of inertia now. Now, if you look at this simple expression, it just tells you that the total mass of the black hole is at the Schwarzschild radius and nothing else. Now, the coefficient in front is exactly 1. So total mass is located at Schwarzschild radius. Now, since the Schwarzschild black hole is perfectly spherical, then this means that it must be a shell structure. And according to the external energy paradigm, there's no energy and matter inside the black hole, right? So we have to come to the conclusion that the Schwarzschild black hole is indeed a hollow spherical shell, but in curved space-time. Now, so this is a new result. Now, when you see this cannot be the singularity, because the singularity does not have a moment of inertia. Now, that moment of inertia cannot be calculated in the ordinary way by using such an integration. Now, because the mass density is not well defined in general relativity, and also distance in curved space is very complicated. Now, if we go back and look at the exact formula again, we see the following structure here for a rotating black hole. The moment of inertia is some coefficient times the mass times some radius squared. And this formula is simply the formula of the moment of inertia of a shell with a certain thickness. And this radius would become the outer diameter or the outer radius of the shell. Now, just to show some numbers here, if we use the final black hole of the first detection with this mass, 62 units, spin parameter, 0.67, then the outer radius would have a size of 186 kilometers. And the horizon radius has a size of 162 kilometers. And in between, we have a thickness, which is about 24 kilometers. Now, this is an effective shell. Now, but for a rotating black hole, we also know there's an ergosphere, which is outside the black hole. So the shell is something like the ergosphere. So this hollow mass shell is an intrinsic property of the Kerr metric, and it always exists in the Kerr solution. So this is not anything added to the black hole. Now, also, the shell provides a physical surface where electric charges can aggregate instead of hovering at the horizon without cause. Now, you see, this is what happens when you have a Reisner-Nordstrom black hole. The charges are outside at the horizon, and there's no physical reason why they can just stay there. Now, there's a shell where they can actually stay in a natural way. Now, also the shell has the electrical properties of the membrane paradigm for black holes. In addition, for the shell model, we don't need an exotic space-time like anti-de Sitter space-time in the interior. Okay, so we believe the black hole is physical, and the moment of inertia is a down-to-earth way to find out the structure of the body. Now, so the paradox of black holes appears because geometry and coordinate transformations are over-promoted. Physics is always about energy and momentum. Now, with this result, we can resolve several major paradoxes in black holes. First is the area paradox, and the result shows why entropy of a black hole is proportional to the area and not to the volume, because all matter particles are at the surface. The volume is not relevant. No. Okay. Well, then we have the singularity paradox. There's no singularity inside the black hole because particles cannot exist inside the black hole. Now, the information loss paradox. There's no information loss for a black hole because information carried by quantum particles is stored at the surface. Well, they're not really lost. And for the firewall paradox, we can conclude that there is a firewall for a black hole, which is the shell surface, because infalling particles cannot cross the horizon. So if you like, these paradoxes are gone. Okay, 2 more minutes. Okay, so these paradoxes, which have perplexed physicists for the last 50 years, become non-issues. They can be simply explained by in a single stroke with the external energy paradigm. And the mystery of the black hole are really created by adopting the point mass, which allow external particles to reach the origin of the coordinate system to form a singularity. Now, so the point mass is the original sin in physics. Now, so here's a picture of the black hole, a Schwarzschild black hole, if you like. And we have two simple formulas here. The energy is mc squared, and the rotational inertia is mr squared. So I like to finish by quoting René Descartes. We're going to understand more and more about black hole, and he said a long time ago, there's nothing so far removed from us as to be beyond our reach, or so far hidden that we cannot discover it. All right, so thank you.
Okay, thank you. There's questions, comments?
So if you have implosion of a star after supernova or collapse or whatever, so it means that you are forming hollow black hole inside, everything is pushed outside or what?
Yeah, for some reason, there's no material inside.
Yeah, it was inside that place.
Yeah,
so
before
this place
it was
becomes
inside.
redefined.
Yeah. Now
So
we
are making something with coordinates. So is it?
no, you see, we don't understand that process, but the result is this here, which is true. There's no approximation. There's nothing added to it. It just follows from the Kerr metric. So we
it's
have
mathematics, but what is going
right.
on?
Now let me give you another example. Suppose you start from a spherical shell dust far away.
This I know.
Initially. So when they collapse, they will eventually just reach the horizon at infinite time, and you will just see a shell there.
But if you are looking from outside, if you are observer which is falling, then you will reach it.
That's right. You observe
So if you are
from outside.
falling yourself,
Yeah.
it's not
Now
the case.
the problem with the other interpretation is observer inside will see something different, but there's no observer that goes inside and tell you what happens.
Imagine somebody was sitting in the star.
Yeah. Well, you see, he's not going to tell you anything. All right.
No, but you say
now,
that
so
it's hollow, so it does not
so
exist,
so
but it
you
was
you
existing.
cannot make any conclusion with that. That's the issue.
So that's what. So in the modern picture of quantum field theory, Hawking radiation can be understood as a Bogoliubov transformation close to this black hole. In your picture, Hawking radiation would not exist.
Well, it does exist. Why doesn't it exist?
So it's okay.
Yeah, it's perfectly fine.
With Hawking radiation,
Right.
it should be okay.
So the shell must be very hot too. It will radiate
It's only
also.
differently explained, a little bit. Only early comers are stuck later. They are all.
No, there is
all these
Hawking
photons are
radiation.
stuck to the horizon.
Okay, I think that's an interesting discussion to be continued. Is there another important comment or question? Here.
Similar, like a little bit evaporation of some rays or something.
Yes, it's a very interesting point of view. And we notice this property when you have falling, a shell falling. And then you can even see on the horizon the induced charge of an electromagnetic structure by charge being accreted. This is the beautiful work that Rick Haney did.
Right. Now you also did some work on this.
Well, well, the mass formula is mine.
No,
therefore
and
I
also
know.
with honey.
Yes,
Right.
the mass formula is mine.
Right.
Patrice
Okay.
de Doulon.
All right.